This week, we are going to be taking a bit of a shift into relativity, actually. Um, but to get there, we're going to do a little bit of a pit stop first, which you can see from up here, something called bosons. We're going to briefly go over those. They're not really related to relativity, but I need a place to talk about them, so here we go. um, and so, your warm up question is something that I think I've said specifically before, but I'm not sure. But either way, if you don't remember the specific answer, just kind of think about it. I'm curious what your answer is for this. And that is light matter? Okay, is it what you would consider matter? There is a technical definition of matter, and you can say this is matter, this is not matter. So is light matter? Kind of curious to see what you could say for that. And yeah, all you need is just yes or no in this case. So, light is not matter. Okay, so the answer is no. But there is a light particle. Okay, so light is not matter, but it is a particle. So, what's the definition of matter? Matter is anything that is made up of subatomic particles that have mass. Okay, that's an actual definition of matter, that it has to have mass. Light does not have mass, but it is made up of a subatomic particle. So that's kind of getting into what bosons are. So remember, when was this? This was back in January. We talked about a bunch of like quarks and stuff, right? And these are defined as fermions. Okay, and we had, here, let me kind of create a little table here. So we had quarks, which, let's see, we had, how does it look? There were three generations of them, and then there was a plus 2/3 charge. There was minus 1/3 charge. And so you had an up quark, you had a down quark, you had a charm quark, strange quark, a top quark, and a bottom quark. And then you also had leptons, which were either minus 1 charge or 0 charge. And you had electron, muon, tau, and here you had neutrino, the electron neutrino, the muon neutrino, and the tau neutrino. Okay, so you had these 12 particles, and these together are the fermions. Okay, so that's what these are. Why am I supposed to like that? Okay. So this is what we kind of went over before. I said, hey, here's what they are, here's the things, there we go, blah, blah, blah. So anything made up of these particles, and also antimatter versions of these, which are things as well, is considered matter. Well, again, antimatter would be antimatter. But yeah, so that's all matter. But that's not all of the particles. So there's another set of particles called bosons. So fermions. Let's see. Subatomic particles that all have mass, aka matter. Okay, so bosons are subatomic particles that do not have mass. So, however, what do they do then? So, instead, what they do is they propagate forces. Okay, so oh, it's PA. Propagate. Yeah, okay, that's right. So what do I mean by that? What I mean is that there are forces within the universe. Again, of course, even just this unit, we've talked about gravity a lot. That's a force that is throughout the universe, and so there is a boson that would basically is in control of gravity. Okay, so whenever there is a gravitational force between objects, there are bosons that are being exchanged between those. Similarly, there's also electromagnetism or light. Those are also the same kinds. Those are all kind of together. There's a particle that's associated with that. That one you probably know about that one, and there's also a couple others that I believe I've mentioned before as well. So the the first one of these I'm going to go over is the one that you've probably heard of before, and that's the photon. Okay, the photon is the force particle for electromagnetism and light. Okay, so those are together. So photons, we again remember in Unit 6 we talked about how light is a wave. It's also a particle. It's confusing how it's apparently both at the same time. Yeah, that's just the nature of reality. All of these are the same kind of manner, though. Okay, so light is a wave and a particle. Gravity is a wave and a particle. Supposedly, again, I'll talk about that in a second. Yeah, so photon is the one that people have probably heard of before. It's the one that's like, okay, sure, it's the particle for light. All right, fair, right? That was not so complicated in that sense. Next I'm going to talk about is actually the gluon, which is the force particle for the strong nuclear force. So I think I mentioned this again back in Unit 5. And the strong nuclear force is what keeps an atomic nucleus together. Okay, because again, an atomic nucleus, you have positively charged protons. They're all kind of stuck up next to other positively charged protons. So how do they stay together? And that's you have this extra strong nuclear force that is more powerful than the electricity kind of between the positive charges. The thing is that it only interacts over very, very tiny distances. So yeah. And the particles that work for that are called gluons. There's apparently like a bunch of different types of gluons. I think there's like 38 or something ridiculous. And I think it's just by like, for example, there's one of them that's just proton with proton. There's a different one that's like proton and neutron. Then another one that's neutron and neutron. And like, so I think that's how it works. And then of course it also works with the quarks as well. So an up quark and an up quark, and a I don't know, top quark. You know what I mean? So like it all combines everything together. So I think that's why there's multiple versions. I'm not 100% sure, but basically they're all just called gluons. So yeah, those are the particles for the strong nuclear force. Now, there are also W and Z bosons, which are force particles for the weak nuclear force. Now, again, there's multiple versions of these. Like I think there's a W plus, a W minus. I don't really know what the specific difference is. Like, what is the difference between the plus and the minus for W? What's the difference between the W's and the Z's? I don't know, but they are in control of the weak nuclear force, and that is what determines nuclear decay. So the fact that you have this atomic nucleus will decay after this amount of time, this one will decay after this amount of time, this one won't even decay at all, that is controlled by, again, interactions between W and Z bosons for the weak nuclear force. Now, then, of course, we have one more force here. It's the graviton. Now, the graviton is, as you can probably guess, the force particle for gravity. However, it's not actually confirmed to exist. And so what I mean by that is that every single model that we have in terms of dealing with force particles like this says this should exist. But we have not specifically detected the particle by itself. Okay, we have detected photons by themselves. We've detected gluons by themselves. W and Z bosons by themselves. We have not detected gravitons by themselves. And so there is a potential issue there where maybe they don't actually exist, and then that's a problem. Okay, so that is an issue that we don't have it to be 100% confirmed to exist. But at the moment, there's no reason to assume they don't. The easiest thing to assume here is that we just haven't managed to find them, just because we haven't, right? So that's a possibility. It's totally a possibility. Now, there is a possibility that there just isn't a graviton, in which case that's weird, because that sort of throws our entire knowledge of particle physics sort of out the window, because it's supposed to exist. So yeah. But for now, we are going to, kind of assume that it does exist. Maybe you, I don't know, look back on this in a decade or so, and this is completely different, but who knows? Now, if you've heard the term, so again, boson is the group name for all of these kinds of things. Okay, similarly to how the fermion is the group name for all of these kinds of things here. So, but if you've heard of the word boson, you've probably heard of it in the context of something else, where you've heard of the Higgs boson. You may have heard of this. This was a big thing 5-ish years ago. Um, the Higgs boson is complicated. I'm gonna give you a super generalized way of thinking about it. There'd probably be some like grad student or professor, whatever, or researcher who would be like, "Oh, what you're telling them is totally wrong." But like, I'm gonna say it this way anyway. Um, the Higgs boson is generally thought of as the particle that gives other particles mass. Okay, so the fact that the fermions have mass, but like photons don't have mass, gluons don't, none of these have mass. The idea is that the Higgs boson, because the Higgs boson interacts with these, but not these, that's why these have mass, but these don't. Okay. Um, Now, I did kind of separate it a bit because there is a difference here in that forces, electricity, gravity, all that kind of stuff, forces are vectors, right? They have a direction and a magnitude. Mass doesn't have a direction. Mass is a scalar. So there is a whole other element of this where, again, remember how I said there is fields with this. There is a electromagnetic field. There is a strong nuclear field, a weak nuclear field. There is a gravitational field. There's all that kind of stuff. So the particle, wave, field, all that kind of stuff works together. So you could sort of think of it as like there is a Higgs field that again deals with mass. But generally, these are described as vector bosons or like vector fields or something like that, because again, there's a direction. While this is described as a scalar field or a scalar boson, because again, it's just mass is mass. And again, this gets very complicated into like tensors and stuff like that. A tensor is basically a multi-dimensional vector. So a vector is just a lot. It's an arrow, right? It's saying here to here, straight line pointing in this direction. A tensor is basically okay. Let's have like a plane or a 3D shape that actually has a direction. So that's its own different thing. It's very complicated. I'm not going to get into how this all works. This is like very high level math and physics stuff. That's kind of insane. But that I just want these names to be in your head, and I want this whole sense about like, okay, this particle is this force, this is that force, and I just want you to kind of know about this and know that these exist. And so with these together, you generally these let's see, how many of this? If 12, so these 17 particles together are usually seen as the standard model. So if you ever look at, for example, go on Wikipedia. Look at the standard model. Yeah, standard model particle physics. You can see what we have here. So you can see here's your 6 quarks. Here's your electron, mu, and tau, and the associated neutrinos, and then you have your bosons. Yeah, W and Z. Again, for some reason, the graviton's not on here. And again, that's because it's technically has not been confirmed to exist at the moment. Yeah, see, gauge boson's another term for it. And then here's scalar boson, there's your Higgs. So, yeah. That's, again, the idea about how this stuff works. Is there actually a thing about... Because now I'm curious. Graviton. The eccentric Charles. Okay, yeah, so this shows, like, what everything interacts with. What is the black thing, actually? Is that the graviton? That's a photon. Right, that'd be gluon. What is it? I don't know what this crap is. Okay. Yeah, so here, again, graviton. Yes, here's your weak force, electromagnetic, strong force. Again, so there's apparently other things. Again, there's, of course, more stuff with all of this. Oh, Z0 is apparently the name. Yeah, graviton hypothesized, blah blah blah, strengths and all this stuff. We're not going to get all the numbers and crap. That's not important. Yeah, an elementary particle that manipulates the force of gravity. So same kind of idea, but again, it's not complete in terms of the stuff. It's sort of a theorized thing. it should exist, but it currently doesn't. So, yeah, that's sort of the deal with that. Now, one thing that's interesting to kind of go off of this, and how this actually does relate a little bit to relativity, though very slightly, is that we have talked about, of course, throughout all of this, the speed of light. Okay, the speed of light, 300 million meters per second, and all the stuff associated with that. Now, really, more accurately, the speed of light, which is 300 million, that's I forgot zero. More accurately, the speed of light should be called the speed of bosons. So because all bosons move at this speed. So what this means is that photons, gluons, W and Z bosons, gravitons, and presumably the Higgs boson, they all move at the speed of light. So what this means is that the corresponding forces also move at the speed of light. So in other words, gravity moves at the speed of light. Okay? So, for example, what if the sun were to disappear just right now? Okay? Now, because of the speed of light, it would take about 8 minutes for like the Earth for the light to stop hitting the Earth. So if the sun were to disappear, we would not know about it for 8 minutes. In addition, though, the Earth would still continue to orbit as if the sun was there for another 8 minutes, and then it would continue. It would just start moving tangentially to that. So it all these all are by the speed of light. Again, you should probably say speed of bosons. And in fact, since one thing that's interesting, and this sort of again gets into relativity, we'll talk about this more later tomorrow, is that kind of by how this works is, again, remember these don't have mass, right? The Higgs boson does not interact with any of these. So one way to think of it is the speed of light is actually the speed of no mass. If you do not have a mass, you move at the speed of light. Okay, so none of these have mass. Then they move at the speed of light. So that's sort of the basis for that there. And again, some interesting stuff comes from that then, where you kind of say, okay, well, if I have a thing that does have mass and I try to move it at the speed of light, what happens, right? And so that's kind of what we're going to get into going into tomorrow from that. However, now I want to just move on to the basic sort of definition of relativity. Now, the relativity that people think of in terms of like, the fancy Einstein stuff, that is special relativity and general relativity. Now, those, again, are specifically talking about how objects move and behave relative to the speed of light, and these are effects that basically manifest. They're always there, but they're not really noticeable until you get close to the speed of light. So that's sort of the specific instance there. But there's a general term of things being relative to each other that we also should talk about. Okay, so physics as a whole, again, the idea is we're taking math, we're taking kind of laws of the universe, and we're basically saying this is how it is. This is the absolute reality of the situation. Okay, so physics likes talking about the universe in terms of absolutes and clear answers. Okay, for example, think back to the beginning of the year. If you roll a thing down a ramp, and based on how long the ramp is and the angle of the ramp and like the frictional coefficients and that kind of stuff, you can very accurately predict the exact speed of how fast the thing is going to move, and you have that answer. It's not if you keep putting that ball on the ramp or whatever in the same position every time, it's not like the numbers you're going to get are suddenly wildly different every time. You have, this is the answer. This is this rule, this equation come together to give you this answer, and that is the correct answer. Now, we already have a little bit of a weird thing about that because we talked about radioactive decay and how there is not a very clear thing about like when a thing will decay. We have the half-life, but that's sort of a statistical average of talking about decay. Again, I mentioned how if you stare at one atom, you don't know when that one atom is going to decay. You just know that like half of a sample will decay after the half-life time. So you can still say that's still following a clear rule in that, okay, we don't know when this one thing will decay, but we know that, again, you have this statistical process that's described overall, blah, 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 there you go. But there's still, even if we talk back to the first scenario and talk about like speeds and stuff like that, you think, okay, that's again very obvious. So what's kind of the issue here? The issue is it's not necessarily the same. Okay. Um, and now some of this is, you know, might seem kind of trivial. And so here's a common example. Let's say you are driving on the freeway at, I'm going to use the imperial system. Oh no, 70 miles per hour, and pass a car moving 60 miles per hour. Okay. Now, is it fair to say that you could also describe this physically, in terms of physics rules and speeds and stuff, that if you were moving at 0 miles per hour and the other car was moving at negative 10 miles per hour, is that still an accurate description of the speeds compared to each other? And the answer is yes. Okay, you could describe your speeds as you moving at 0 miles per hour and the other car moving at minus 10 miles per hour. Now, this is a fair way of describing it. Now, is this necessarily helpful? It depends, right? Because the first example, the 70 mile per hour and 60 mile per hour, those are speed descriptions compared to the road. Okay, so if you want to know, for example, how much time will it take for you to travel 10 miles, then those numbers matter, right? Because then you're talking about, well, I'm talking about how long does it going to take to travel 10 miles of road, so I want to know what my speeds are compared to the road, right? Obviously, saying, oh, I moved at 0 miles per hour and the other car moved at negative 10 miles per hour, and then you try to figure out how much distance you traveled, then it's not helpful. It doesn't give you the right answer. But if you care about, like, for example, let's say after an hour, how far are you from the other car, then the 0 and negative 10 miles per hour speeds work fine, because then you're talking about distances of the cars, whereas compared to each other, well, as these speeds are the speeds of the cars compared to each other. Okay, so those are fine. So the key is for this is that both of these descriptions use speeds compared to different reference frames. Okay, so in the first example, the reference frame is the road. You are traveling 70 miles per hour compared to the road. The other car is moving 60 miles per hour compared to the road. The second example is the reference frame is yourself. You are moving 0 miles per hour compared to yourself, and the other car is moving negative 10 miles per hour compared to yourself. So both of those descriptions are fine. It's just that the questions they answer, you have to be careful sort of in which reference frame is actually important for the question you're answering. Again, it would not make any sense to use the reference frame of yourself when talking about how much distance have you covered on the road. That's sort of that's pointless. There's no reason to, there's no reason to describe a question like that. However, in both instances, you could do the math to figure out again, after an hour, what is the distance between you and the other car. Okay, you could do that, and with both of these sets of speeds, and you would get the same answer. So you might think, okay, I mean, sure, I have different numbers, but they're basically just different ways of describing the same instance, right? It's not like the result is different, right? In both cases, I would be, 10 miles ahead of the other car, okay, after an hour. So it's not like, sure, you solved them in different ways, I guess, and you use different numbers to get there, but at the end of the day, the result is the same, okay? It's not like one set of numbers gave you one answer and the other set of numbers gave you a different answer. It's not like let's say using the first numbers, oh, I'm 10 miles ahead, but the second answer, I'm 20 miles ahead, right? It doesn't happen, right? Reality is what it is. You are a certain amount of distance ahead of the other car, so regardless of how you get there, it doesn't, you know what I mean? So it's like, you might think, what's the point? Why are we even talking about this? I mean, sure, I guess it's a thing, but like, so what? Who cares? Because you can get situations where that doesn't actually happen like that. So let me actually kind of draw something here. My great paint skills. Let's say What is the thing? Okay, that's fine. Let's say you have. Let's say here's a train track. Okay, it's a very straight train track, and you have. Let me just draw one car because I'm lazy. Really, I can draw good. I mean, I guess this could be any sort of car. So, and there's a person. That's terrible. Hold on. Try how to be a little bit better. Okay, this is a deformed person in the car, and the car is moving this way. Okay, train track, the car. There's also a person who's standing outside of the train tracks, outside of the train car, just standing, on the side of the road or whatever. Ooh, there he is. Okay. Now notice that like they're the same. They're lined up. Okay, so that's important there too. Now let's say you have two lightning strikes. Okay, there's one, and there's one. Okay, and let's also say that this distance and this distance are the same. Okay, let's say those distances are the same, and let's also say that these distances are the same as well. Okay, so those distances are the same. I'll label this as D1. This is also D1. And this is D2. This is also D2. Okay, so those distances are all the same. So let's think about this. If these two, if these both are the same distance, and this person here, if this guy here, if let's say he's staring out and he sees these two lightning bolts hit at the exact same time. Okay, he sees them strike again. Let's say he has like incredibly good timing skills with his eyes or whatever, and he knows, yes, I know exactly that those two, I saw the light hit my eyes the exact same time. Therefore, the lightning strikes occurred at the same time, right? That makes sense, okay? So that seems pretty clear from this person's perspective. Now, you might think, okay, well, if that's what this person saw, then this person should see the same thing, right? Because, I mean, sure, these D1 and D1 is not the same as D2, but these distances are the same as to each other. So he should also see the same kind of thing. But hold on, light takes a little bit of time to get from the lightning to the person's eyes. In this amount of time, this train car has moved a little bit to the right. A little bit. It's not anything that, like, a human would actually notice, but technically, because this train car has moved a little bit to the right during the time it takes for the light from the lightning bolts to get to him, this distance is actually not going to be the same as this distance over here, as this distance here, by the time the light actually gets to the person. So what this means is that if this person here sees the lightning strike at the same time, this person will not see that. This person will see that this lightning strike hit first, and then this one hits second. So we have a situation where the only difference is, again, in talking about speeds relative to each other, the only difference here is the same. It's the same kind of setup as the whole car in the freeway scenario, but one person sees something happening, two events happening at the same time, and another person does not. One person sees two simultaneous events, and another person sees two consecutive events. So in other words, depending on the way you're looking at this, your perception of reality is different. It's not the same. So this is the basis of relativity in the general sense. You can have scenarios where, depending on your reference frame, you can perceive reality differently. Okay? This is weird. It's basically saying, and the question is, well, what actually happened? Did lightning strike first? Or did they strike at the same time? Did it strike one after the other? And you might be tempted to say, well, the person who's on the Earth saw it strike at the same time. The other dude was moving. Okay, but like the Earth's not stationary. The Earth's moving too. So how do you know what I mean? It's like, how does this even work? And so this gets into the whole idea of relativity, that things are relative to each other, and that a lot of times there isn't really a very definitive answer in a lot of these kind of scenarios. Um, and it's really weird to think of that. And again, this gets the whole thing about special and general relativity is that this gets pushed to actually like very, weird and extreme instances once you start getting towards the speed of light. Because again, the whole thing of lightning strikes, like that doesn't, this actual example in real life, who cares, right? This is just sort of an interesting thing to notice, but it's not like your life is different because of this. You know what I mean? It doesn't really happen that way. But um, that's not true if you actually start to move towards the speed of light, because these effects get worse, more extreme. So, I know this has been kind of short, but again, we're going to really get into the math behind relativity stuff with that tomorrow. So, I'm actually going to all the way just jump to the wrap-up question. And your wrap-up question is just, what is your speed? Right now, what is your speed? And the thing is, whenever you're describing your speed, and we technically should have been doing this all since the beginning of the year, you have to say, what is the speed relative to? So, put down an answer that you have for that in that case. So, there's many answers you could put here, right? You could put basically there is pretty much an infinite amount of answers you could put here. The most simple one is say my speed is 0. I'll use meters per second relative to, I don't know, the ground, the chair I'm sitting on, etc. Right? So there's a bunch of things you could say that you're 0 meters per second relative to. For example, I'm moving at 0 meters per second relative to the tree that I see out the window, right? At least the trunk of the tree, anyway. I mean, maybe some of the leaves are moving a little bit in the wind, but I can't see that from here. So, I'm moving 0 meters per second, probably relative to the what's that building called? The Petronas Towers in Kuala Lumpur, Malaysia. Okay, probably. I mean, I guess there could be a little bit of motion in the Earth's crust between me and there. Um, so in terms of something that's on the Earth's surface, then I'm probably moving at 0 meters per second. But I could describe something else. For example, I'm sure I'm not 0 meters per second to relative to most other people on the Earth, right? Most other people of the Earth are probably moving around to some degree. Maybe not a lot, but probably a little bit. So that's definitely so. I guess more people are not moving probably with the lockdown stuff than normally, but still, there's probably lots of people who are moving around at least a little bit. Um, and of course, like animals, that's not true. But again, you could go further than that. For example, what is this is all relative to the Earth. For example, I could say, well, what is my speed relative to the moon? Right? And that you have to base on a couple things. You have to base on the fact that the Earth is rotating. The moon is also going around the Earth. And the moon is also actually moving a little bit further away from the Earth, like over, a couple like centimeters a year. But you could say, for example, what is my speed relative to the center of the Earth? And I think that's like 500 meters per second, so relative to the center of the Earth. Because again, the Earth is rotating, so that's about what that is. Also, this number is different depending on what your latitude is, because as the equator is where you're spinning the fastest, and at the poles you're technically not spinning at all if you're exactly at the poles. but for our latitude level, I think I calculated this a bit ago to be about 500 meters per second. Um, but you could also ask, what is your speed relative to the sun? And, well, that's, of course, the Earth is moving around the sun, in which case that's about 30,000. So that's something. You probably would want to say relative to the center of the sun, actually, because the sun is also rotating around. I believe every like 11 days it rotates. I think that's what it was. I have to go check. I don't remember. Um, there's that. But you could also say, okay, what is my speed relative to the center of the galaxy? Because the solar system as a whole is moving around the center of the galaxy. So in that example, I believe the number is about 200,000 meters per second. Center of the galaxy is a black hole called Sagittarius A star. So there's that. You can go even further though and say, what about my speed relative to other galaxies? And of course, depending on whatever galaxy you're talking about, you could do whatever. But for example, Andromeda. So we're moving about 600,000 meters per second relative to the Andromeda galaxy. Okay, our galaxies are both moving towards each other, and will collide in 4-ish billion years. Again, colliding is sort of, when you think collide, you think two solid objects smacking into each other, and that's not really what happens because galaxies are mostly dust and gas and empty space. So you're not going to have many physical objects smacking into each other, but whatever. So there's that, but you keep going, right? For example, what about, there's another galaxy, there's the Large Magellanic Cloud. That's a galaxy. Or the Small Magellanic Cloud. Or I'm trying to think of other galaxies that I know. There's a galaxy called the Sombrero Galaxy. It actually looks pretty cool. I know there's that one. I'm really bad at like galaxy names. I know there's a ton, but I just don't know very many of them. I don't know. I can't think of any other ones. Like the one I remember is the Sombrero Galaxy. Good for me. But so you could do that. You could do it for that. And even further, for example, added to this is the fact that the universe is self-expanding. So then what, right? And so that adds to all this thing. So all of these answers are correct. And again, you could put in whatever answer you want. You could say, at the moment you're 1 meter per second relative to like your, I don't know, your mom walking by you. You know what I mean? It doesn't matter, right? So the point is, technically, whenever we did any sort of kinematics or forces, we always should have said like relative to something. Now, granted, the implicit thing is that we're talking about relative to the ground. And that's usually kind of assumed, and we don't usually really need to specify that because it's kind of obvious. But sometimes it's not obvious. So sometimes you have to be a little bit more careful about this. And again, especially when we're going to talk about with relativity, then it really does matter. And especially for a question like this, and you could kind of see what the answers could get to be. So that's kind of what I was getting at with this stuff. Okay, you don't really have you don't have any homework questions for this today, but tomorrow we are going to get into some math behind actual special relativity. And it's not as bad as you might think it would be. Because again, special relativity sounds super terrible, and it's Einstein, so and there's definitely difficult stuff in it. But what we're going to be doing is not that bad. So, and it gets to some very, very weird things. So that's what we're going to be doing starting tomorrow.